All right, so the other way that enzymes are affected by their environment is when other substances are in their environment. This can affect the way that the enzyme functions. So these are called inhibitors. And the top part here, the top picture here just shows a regular enzyme and a substrate forming an enzyme substrate complex when they collide, and that substrate is broken into its two pieces, which is making the products. Okay, so it's just like regular, normal enzyme function. But these ones down here show two types of something called an inhibitor. There's two types. There's competitive inhibitors and there's non-competitive inhibitors. And really what this, what determines if it's competitive or not is whether or not it binds to the active site. Okay, so these inhibitors are, these are other molecules that are able to bind to, or in other words, stick to the enzyme. All right. So a competitive inhibitor is one that binds to the active site and it blocks the substrate. So it actually physically blocks the substrate. So you can see here, here's the active site, right? The substrate has a shape that is complementary to the active site, but so does the inhibitor. The inhibitor is able to take the place or block the substrate. So now the substrate is not able to get into the active site. And of course, if the substrate can't get into the active site, then you don't have any reaction that happens, right? You can't have a reaction. No products will be formed. So this enzyme then it doesn't act on this inhibitor. The inhibitor just kind of sits in the active site. Now, eventually the inhibitor will fall out and a substrate might be able to get in unless another inhibitor comes back in to block the active site. So these inhibitors do fall in and out of the active site. So it doesn't fully stop. It doesn't fully stop the chemical reaction, but it will slow it down, right? It will slow down. Okay, so the reaction slows down. Okay, now with a non-competitive inhibitor, it's going to bind to a different location than the active site, so not the active site. And what it's going to do is it's actually going to change the shape of the active site. So it's going to kind of interact with the enzyme and change the way the active site, change the shape of the active site. Okay, and then what's going to happen is that the substrate is no longer going to be able to fit. It no longer fits in the active site. And that's how the substrate gets blocked. Okay, so in other words, the active site is no longer complementary to the substrate. So again, here's the active site, right? It fits, it's complementary to the shape of the substrate. This is a different location on the enzyme. This is not the active site. This is a different site. It actually has a name. This is called the allosteric site. So an allosteric site is any pocket on the enzyme that is not the active site. And if you look, the allosteric site is complementary in shape to the inhibitor, isn't it? And so now if the inhibitor sticks onto the active site, then what happens is it changes the shape of the active site, and now this shape is no longer the shape of the substrate. And so the substrate cannot fit into the active site because it's no longer complementary. And again, if the substrate can't fit into the active site, then it cannot make product. So no reaction will occur, or fewer reactions will occur. So again, the reaction slows down. Activators are similar. They just do the opposite thing. So an inhibitor will turn off the enzyme, but an activator will turn on the enzyme, essentially. So again, what happens with an activator, this time it has to be at the allosteric site, right? So it's also known as allosteric activation, because it has to happen at a different site, right? Here's the allosteric site. And it has to happen here. If it were to stick into the active site, then it would be an inhibitor. It would be blocking the active site. You can't have the activator blocking the active site. That doesn't make any sense. But what you see here is the active site without the inhibitor, or sorry, without the activator, is not complementary to the shape of the substrate. So here's the substrate. And you can see the shape is all squiggly here, but it's not here. It's smooth here, right? Now when the activator, so here's the activator here. When the activator sticks into the allosteric site, then what happens is it changes the shape of the active site, but now the active site fits the substrate. So now the active site changes shape in a way that fits, that is complementary to the substrate. And so now the substrate can fit into the active site, and the enzyme will form an enzyme substrate complex, and then what you get is product over here. Products are made. So without the activator, then the enzyme doesn't function. Okay, now another thing that will affect how fast a chemical reaction occurs that includes an enzyme, so how fast an enzymatic reaction happens, is the substrate concentration. Okay, remember that another word for substrate is a reactant. So, and then concentration, in case you don't remember, concentration is equal to mass divided by volume, right? So the amount, like the quantity of something in a certain volume of liquid. And the rate of the reaction, remember we can measure rate of reaction. We're talking about the rate of a chemical reaction or an enzymatic reaction. Remember there's two ways that we can measure this. It's the amount of product made per unit time. I should do this. Made per divided by time. But the other way that we can measure this is, the other way that we can measure this is the amount of, substrate, let's say substrate used divided by time. Right, so we can measure either the appearance of the product or the disappearance of the substrate. Okay, now what happens is that when we're looking at this graph, here, we're looking at, this isn't one reaction, this is many reactions that are graphed with a line. So let's put in some data points here. So let's say that we tried the chemical reaction here with this much substrate concentration, then we tried it again with this much concentration, then we tried it again with this much concentration, then again, then again, and again, and again. Okay, so what's happening here is this is reaction 1, this is reaction 2, this is reaction or trial 3, this is reaction 4, this is reaction 5, and this here is reaction 6. Okay, and what this experiment is showing is that when the concentration of enzyme is low, right? When the substrate concentration is low, then the rate is also low, right? Low rate. So in other words, it's not producing a lot of product per second. Okay, but if we add a little bit more substrate, well then it turns out that that actually helps the rate of the reaction. The rate of the reaction is a little bit faster. And if we increase the substrate, again, if we increase it some more, increase the substrate amount a little bit more, then the rate speeds up. So for a while, increasing the amount of substrate will actually produce more product per unit time. So if we're measuring every second, then the amount of product per second is increasing as you do this reaction over and over again, as you repeat this reaction with more and more substrate concentration, with a greater amount of substrate in the same amount of volume. But what you'll see is that over time, or sorry, not over time, as you kind of there's a limit that you reach with substrate concentration. So there's kind of a point where now, look at the difference here between these two rates. The difference is decreasing, and there's even a point where, like here, where now there's no change at all between reaction 6 and reaction 5, right? Like these are basically the same, right? So increasing the substrate concentration in a enzyme reaction will increase the rate of the reaction for a while, but there will be a point where you reach a maximum rate, and adding more substrate will have no effect. Okay, so beyond this point, adding more substrate has little to no effect. So why is this? Well, if you look in this part of the graph here, where increasing substrate concentration does have an effect, a lot of those enzymes are empty. They're actually searching for a substrate molecule. And so by adding more substrate, we are increasing the chances that an enzyme will bump into a substrate to form an enzyme substrate complex and make product. So as we now here in this one here, look, we've got more of the enzymes are holding on to a substrate, which means that this enzyme and substrate will make product. So more product will be made per unit time, per second, or per minute, because more enzymes are finding substrate easier. So the enzymes are finding the substrate a little bit easier, which means that more product is being made. But in C, what we find is that it doesn't matter if we add more substrate, because the enzymes are actually all full of substrate, and therefore we don't need to increasing the amount of substrate. It doesn't matter, because all the enzymes are already at their maximum capacity, which means that they're not able to bind onto another or to stick onto another substrate. Okay, so they're already making, in this one here, they're already making as much product as they possibly can, because all the enzymes are saturated. They are full of substrate. So here we could say that in this one here, the enzymes are working as fast as possible. Okay. Now the same is true for enzyme concentration. If we add enzyme to the reaction, you might start with oh, sorry, this is substrate concentration as well. Never mind. So this is just another way of showing substrate concentration. But the same is true with enzyme concentration. You can add enzyme to the solution or to the reaction, and at first, when you have really low enzyme amounts, so if we do this here, let's see here. Let's make our own graph. So on this side over here, this is the reaction rate, and the reaction rate increases up this way. And this down here is enzyme concentration, and it's increasing that way. If we do this reaction 1, reaction 2, reaction 3, reaction 4, reaction 5, reaction 6. Okay, let's say this is like 1, 2, 3, oh wait. 4, 5, 6. So maybe this is, let me see here. So these are, if this is reaction 1, 2, 3, 4, 5, 6, each reaction is going to be a reflection of enzyme concentration. Okay, I just want you to make sure that you understand that enzyme concentration is increasing going this way. So like reaction 1, in reaction 1, let's say, reaction 1 has, let's say it has 0.1 millimole per liter. No, not millimole. 0.1 units per mil. Let's say like that, okay? And in reaction 2, maybe it has half a unit per milliliter, half an enzyme unit. And in reaction 3, it's got 1 unit per milliliter. And in reaction 4, it's got 1.5 units per milliliter, okay? And so on and so forth, 5 and 6. Maybe it's 2 and 2.5 units per milliliter, right? Units per milliliter. Okay, and so what happens initially, again, is that the rate of reaction starts increasing until it gets to a certain point, and then it kind of flattens out. Okay, so it kind of goes up, and it flattens out. Can I hold that? Oh, not bad. Kind of like that. Okay, so at here, this was a low amount, a little bit more enzyme, a little bit more, a little bit more. And so after a certain amount, there's not very much change. It doesn't affect the speed of the reaction, right? So the difference between reaction 1 and reaction 2, there's a lot of difference. And 2 and 3 have a lot of difference. And 3 and 4 have a lot of difference. But once we start looking between reactions 4 and 5 and between 5 and 6, there's not a lot of difference in how fast that reaction is happening. Okay, so the same thing is happening there with enzyme. All right, you guys, and so that kind of talks about the different ways that we can change the environment to affect the speed of an enzyme or reaction. We've got inhibitors, competitive and non-competitive, activators, and then we've got the effect of substrate and enzyme concentration on the rate of the reaction.